Today I am starting module 11 of the subject plate and shell, and it is the first lecture. So far I have discussed the shell theory, especially the membrane theory of shells in application of surface of revolution. So, you have seen that a spherical dome and then a pressure vessels or a tank of any arbitrary meridian have been analyzed using the membrane theory of shell. Now, a very common type of shell exists in application, practical application, and that is the cylindrical shell, that is used for roof structure, especially for workshop and warehouses, and this type of structures, cylindrical shell, is an example of single curve shell. That means, a generator which is a straight line is moved over a plane curve, that is called directrix, and as a result the shell is formed. So, single curve shell means it has Gaussian curvature 0. So, you can see an example of cylindrical shell, a large span has been covered with the help of very thin structural element, which is a form of cylindrical shell. This is also called single barrel shell. Now, multiple barrel shells are also common in nature. Cylindrical shells, you can see it is actually the singly curved shell whose Gaussian curvature is 0. So, Gaussian curvature 0 means the product of two principal curvatures, that is 1 by R 1 and 1 by R 2 is 0. That means, one radius of curvature is infinity. So, that is evident if I take a straight line generator which moves over the directrix, that is a plane curve. So, this straight line generator has infinite radius of curvature. So, therefore, Gaussian curvature is 0. Now, this kind of shell also falls under the category of developable shell. That means, this shell can be flattened into a flat surface, and it is also falling under the category of ruled surface, because when the straight line is ruled over the curve, the surface is formed. So, therefore, it is called ruled surface. It is commonly used as roof in a large span structure. Okay. The cylindrical shell may be of single barrel type, that is, here it is a single barrel cylindrical shell, or it may be multiple barrel cylindrical shell. You can see that cylindrical shell has been provided with the edge beam here. Here the intermediate edge beams are also there. So, it is having multiple support in this in different span. So, these are the exterior support and these are the interior support. So, today our focus will be to derive the differential equations of equilibrium in cylindrical shell using membrane theory. So, let me see what are the elements of the cylindrical shells. Here the cylindrical surface is shown and the dotted lines are the directrix. So, directrix may be of any form, any general curve can be taken, or any known curve, say circular arc or a parabola or a elliptical curve can be taken. Then you can see that shell is supported at the ends by some kind of structure. That structure is known as traverse. So, at the end it is supported by traverse, and it may be provided with edge beam or without edge beam also. The straight lines that are rolling over the curve are known as generator, and the curve is known as directrix. Now, if I see the different types of traverse, traverse may be solid diaphragm, a thin structural element which acts like a traverse, it is a solid, no opening is there. So, then the traverse may be of tied arch, that is in the form of arch, but the vertical suspenders are there. Then it may be trussed arch having a truss to join the rib of the arch with the horizontal member. Okay. Now, directrices that are usually employed in the cylindrical shell may be of a arc of a circle. Arc of a circle, that is a circular cylindrical shell, is very common and analysis is also simple because of simple nature of the curve, that is circle. But when we take the elliptical directrix, semi ellipse directrix, or a part of a parabola or a cycloid catenary, the analysis becomes involved because of complexity in the geometry. You can see the circle has the constant radius of curvature, but other curves you will find the radius of curvature varies at any meridional angle. So, that is the point where the difficulty arises in solving the cylindrical shell problem with the other types of directrix. But for architectural reasons, the directrix of other types are also adopted. So, we shall do the analysis of cylindrical shell with different types of directrix: arc of a circle, semi ellipse, parabola, cycloid, catenary, knowing the properties of the different types of curves. Load that I will consider for the analysis of cylindrical shell in this course are dead load, self weight plus live load. So, dead load and live load that are considered together is a gravity load acting on the shell. Then I will also take the snow load, which is a load acting over the horizontal projected surface. Okay. There are various methods of analysis of cylindrical shell. The one common method is beam theory, then second is membrane theory and bending theory. The beam theory is an approximate method. Membrane theory is also simple, but very attractive method because it gives the true picture of stresses except near the supports. Bending theory of course is complicated, that includes the bending moment near the edge of the shell, and that bending theory have been developed including the results of membrane theory. So, let us see what is beam theory. In beam theory, the cylindrical shell can be idealized as a beam whose span is L, and the cross section of the beam is a curved. The curved cross section of the beam is seen here. So, the sectional property that to be used in the beam analysis will be slightly complicated because of the curved cross section. So, that have to be found, that neutral axis of the cross section, moment of inertia about the neutral axis, that have to be calculated for the curved cross section, and other analysis will depending on the beam analysis that we are familiar in our usual strength of material class. So, the maximum bending moment, if it is simply supported shell, then maximum bending moment will occur at the mid span, and if it is supported at the traverse, these are traverse is located here, then maximum shear force will be generated here. So, we can find the maximum bending stress and maximum shear stress, based on which the thickness of the shell and the reinforcement can be calculated if it is used as a RCC roof shell. Then the membrane theory, which we will discuss in today's class, and our whole analysis will depend on membrane theory. In the last module, I will introduce the bending of the shell. So, in this case, the shell is analyzed considering a momentless state. That means, the bending rigidity of the shell is neglected. So, what does it mean? That the shell element is in a state of in plane forces. So, in plane forces are the only resisting forces in the shell to the external load. The external loading is to be resisted by membrane forces, that in a shell element I have shown by arrow. These are the membrane shearing forces and these are the direct in plane forces or membrane forces that you can see. One is in the direction of the generator, that is in the longitudinal direction, another is in the direction of the meridian, that is in the direction of the directrix, that means tangential to the directrix curve, and others are shearing force acting tangential at the edges. So, these are the forces in the membrane hypothesis, and we will take these forces into consideration to derive the differential equations of equilibrium. Okay. Now, in the bending theory of shell, earlier also in some problem I have demonstrated that the membrane theory fails to predict the actual nature of stress near the edges, because the boundary condition of edges was not satisfied. If you recall this, the edge was free in our some of the examples that I took up in the earlier classes, and then due to free edge, the shell at the edge should have 0 stress, but when we use the membrane theory and derive an expression, we found some stresses exist at the edges. So, that is giving a wrong information on the nature of stress that is produced or the stress that is actually produced at the edges. So, therefore, it is suggested that a corrective line load is to be applied at the edge. So, when we apply some corrective line load at the edges, then bending will be developed in the shell near the edges. So, that is the cause of bending. So, bending analysis is carried out in 3 steps. Whatever membrane analysis we have done, this will be used as a particular solution on the bending of shell. So, membrane analysis with the surface load acting on the shell will be used as a particular solution. Then we will do the bending analysis of unloaded shell, because when we will consider the bending moment in the shell, the order of differential equation increases. So, therefore, the characteristic equation will have high order, that means it can go up to the 8th order equation. So, therefore, if we use the unloaded shell analysis, then we will find a equation of the wave and which will get damped out very quickly. So, bending analysis is necessary because of the edge disturbance, and edge disturbance is resulted near the edges and corrective load is applied. So, using these 2 results, that means superimposing the 2 results 1 and 2, we can get the actual boundary condition at the edges, and that will give you the correct analysis of the shell including the bending moment. Let us now go to the membrane theory of cylindrical shell to develop the differential equations of equilibrium. We assume that generator of the shell is horizontal and parallel to x axis. Okay. So, this is the generator which rolls over the directrix, which is a curved. This curve may be a circular arc, this may be your part of a parabola, this may be a elliptical curve, or this may be a cycloid. Various types of possibilities are there for directrices. So, now here our intention is to develop the differential equation of equilibrium. So, we take an element of the shell. The element is taken by cutting from the shell by 2 adjacent generators, 2 adjacent generator you can see, and then 2 cross section perpendicular to x axis. So, the rectangular element is taken whose one side is dx and another side is r d theta. Theta is measured from the crown. This is the crown of the shell, that is the highest point, and from this vertical axis the angle theta is measured. So, at this edge the location is by theta and the adjacent element will be located at d theta, where d theta is small angle. So, naturally the length of this curve is r d theta. So, now the area of the shell element is r d theta into dx. Okay. So, the forces that will be considered on the element to resist the externally applied load are n x, n theta and n x theta. N x is the membrane forces along the longitudinal direction, n theta is the force in the circumferential direction and n x theta is the membrane shearing force that I have shown in my earlier slide, that membrane shearing force. These are the membrane shearing force. Okay. And this is n x directed towards the x axis and this is n theta. So, let us see the free body diagram of the shell element. So, if you see the element of the shell here, the length of the one side is r d theta and another side is dx, which is parallel to the generator. Okay. The capital X, capital Y, capital Z are the component of the load that is acting on the shell in the respective direction. Capital X is the component of the load along the x direction, capital Y is the component of the load along the y direction and capital Z is the component of the load along the radial direction. So, here if we see a differential element, so in one edge this is the stress membrane force N x, which is acting at the middle surface. On the opposite edge the membrane stress is N x plus del N x by del x into dx. So, this quantity is the increment in the length of dx. Now, let me see the forces in the other edges. At the one edge the circumferential force is n theta, at the opposite edge the circumference force is n theta plus 1 by r d n theta by d theta into r d theta. How this quantity comes? You can see the variation is within the length of r d theta. So, therefore, d n theta by r d theta is taken and the length over which it varies is r theta. So, it is multiplied by r d theta. Now, let me see the shearing forces in one edge, that is the edge which is parallel to the circumferential direction. There the membrane stress is here n x theta and in the opposite edge the increment will take place in a length of dx. So, therefore, n x plus del n x by del x into dx is the membrane force at the opposite edges. Let us see the other shearing forces. In one edge where the n theta is acting, the membrane shearing force is n theta x. On the opposite edge it is n theta x plus 1 by r del n theta x by del theta into r d theta. This increment is taking place within a length of r d theta. So, therefore, r d theta term is coming here and it is also multiplied by r d theta. So, knowing the forces acting on the element and component of the loads in the respective direction axis, one is along the x axis and one is along the circumferential axis and one is along the radial direction. So, now we can establish the equilibrium of the forces. So, summing up the forces in longitudinal direction first and then equate to 0. Now, let us see what are the forces in the longitudinal direction. One is n x. So, if I take this direction as the positive direction of the x axis, then n x plus del n x by del x into d x into r d theta, because the length is r d theta over which it is acting. So, it is multiplied by r d theta. On the opposite edges, the force is n x. So, it is n x into r d theta, but the direction is opposite. So, therefore, negative sign is given. Okay. Then also find out other forces in the x direction. Other forces in the x directions are, you can see here n theta x and its increment on the other edges. So, if I take this force first, so that will be n theta x plus del n theta x by r d theta into r d theta into d x, because it is acting over the length d x, and it is multiplied with the force per unit length, because this n x, n theta x and n theta are all expressed in terms of force per unit length. So, therefore, to find out the total force on the edge of the element, we have to multiply by the corresponding length of the element. Okay. Then on the opposite edges, you are seeing that n theta x. Component of the load along the x direction is x, and the area of the surface, middle surface is r d theta into d x. So, total load on the element is x r d theta into d x, and it is equated to 0 to establish the equilibrium. Now, multiplying the terms, that means r d theta, multiplying this term inside the bracket with the r d theta, we will get n x r d theta plus del n x by del x d x r d theta. Then this term is existing as it is minus r x r d theta. Then again we break this term. So, n theta x into d x plus 1 by r del n theta x by del theta r d theta d x. Then we get this term minus n theta x d x, and then we get x r d theta d x equal to 0. So, you can see there are some common terms which can be cancelled. So, n x r d theta is cancelled, then n theta x are cancelled. So, ultimately we are getting an equation of this 1 by r del n theta x by del theta into r d theta x dx plus x r d theta dx, and already this term is there, del n x del x dx r d theta. Now, you can see here with the all terms, the dx r d theta is common. So, dx r d theta indicates the area of the element which is non-zero. So, therefore, divide throughout by r d theta dx. So, after dividing throughout by r d theta dx and after simplification, we get del n x by del x plus 1 by r del theta x by del theta plus x. So, this is the first differential equation that we have obtained using the equilibrium condition in the longitudinal direction, that is the direction parallel to the generators. Okay. Now, in this equation you can see that two unknowns are involved. One is n x, that is the membrane force along the x direction, and another is membrane shearing force n theta x. Because x will be known and r will be known from the given geometry of the shell. So, we have to find this n x and n theta x, but we need other equation, because a single equation with more than one variable cannot be solved. We require the help of other equations. So, now let us establish the equilibrium in the y direction. Y direction, I mean here the direction that is tangential to the directrix. So, you can see the what are the forces in the y direction. One is n theta that is acting here, and on the opposite direction n theta plus 1 by r del n theta by del theta into r d theta. Then other forces in the y direction is n x theta that you are seeing, and here you are seeing n x theta plus del n x theta into del x theta into dx. Okay. Now, establish the equilibrium. So, equilibrium will be established here. One is n theta plus del n theta by r del theta into r d theta dx, that is the total force along this edge that we have taken, then minus n theta dx on this edge, because dx is the length. Similarly, n x theta plus del n x theta by del x into dx r d theta is the force in this direction along the circumferential direction, and on the opposite edges you will get n x theta r d theta, and the total load in the circumferential direction, because y is the component per unit area. So, when we multiply by the area of the element, it will be y into r dx d theta. So, we will get this equation. Now, again term by term multiplication you carry out, and you will find that it is decomposed into n theta dx plus del n theta r d theta dx, then minus n theta dx plus n x theta r d theta plus del n x theta by del x into r dx d theta minus n x theta r d theta plus y dx r d theta equal to 0. Cancelling some common terms are there. So, you can cancel it and divide throughout by r d theta dx. Ultimately, you will arrive at this equation, the second equation of equilibrium, which relates n theta and n x theta. In the previous case, we related n x and n theta x, and here we related n theta and n x theta. So, this equation is 1 by r del n theta by del theta plus del n x theta by del x plus y equal to 0. Now, let us go to resolve the forces along the radial direction and then sum it and equate to 0 to establish the equilibrium in the radial direction. You can see here that if this is the element along the circumferential direction whose length is r d theta, but n theta dx acts along this direction, that is parallel to the direction of generator. So, the total force here is n theta dx. On the opposite edge, it will be n theta plus 1 by r del n theta by del theta r d theta into dx. So, this term is taken n theta del n theta r d theta dx. Okay. Now, resolve the forces along the normal direction. So, if the total angle that is subtended by the element at the center is d theta, then semi angle is d theta by 2. So, when we resolve the forces along the radial direction, suppose this angle is d theta by 2 and this is your 90 degree. So, this angle will be 90 minus d theta by 2. So, resolving these forces along the radial direction, n theta dx cos, because the component of this along the radial direction, if this angle is 90 minus d theta by 2, will be n theta dx cos 90 degree minus d theta by 2, plus on the other side n theta plus del n theta r d theta into r d theta dx cos 90 degree minus d theta by 2. Then the component of the load along the radial direction is z r d theta dx. You can see here the components of the forces on the two opposite edges arising due to circumferential membrane stress n theta is additive, because component are acting in the same direction. So, these are added and it is combined with the external component of the external load along the z direction, that is z r d theta dx equated to 0. So, note it that cos 90 degree minus d theta by 2 is nothing but sin d theta by 2, and because d theta is a small angle. So, we can write sin d theta by 2 is approximately equal to d theta by 2. So, based on that, this quantity will be n x dx d theta by 2, and this component will be n theta plus del n theta r d theta into d theta by 2, and this is as existing here, it will remain z r d theta dx. Now, in this middle term you will find that del n theta by r d theta will be multiplied by d theta by 2. So, that means d theta square will come. So, since d theta is a small quantity, its square is neglected. So, this term can be neglected. So, ultimately neglecting the square of this small term and combining the other terms, because it will be n theta dx d theta by 2, and here also it will be n theta dx d theta by 2. So, that means the component will be 2 n theta dx d theta by 2. So, this component has to be balanced by the component of the load along the radial direction. So, we get actually this 2 n theta dx d theta by 2 plus z r dx d theta equal to 0. So, dividing dx both sides by dx d theta, ultimately you will arrive at this equation n theta plus z r equal to 0. So, this is the third equilibrium equation. Now, we have got 3 equations of equilibrium in the membrane theory for this cylindrical shell. So, 3 equations of equilibrium are these: del n x by del x plus 1 by r, del n theta x by del theta plus x equal to 0. That is first equation. Second equation is 1 by r del n theta by del theta plus del n x theta by del x plus y equal to 0. Third equation is n theta plus z r equal to 0. You may note here that we are dealing with 3 unknown quantities. One is n x, n theta and n theta x. One is n x, other is n theta and membrane shearing force n theta x, because the component of the load will be known from the given loading condition on the shell. Now, it is obvious that 3 equations and we have only 3 unknown quantities, though these equations are this problem of cylindrical shell in membrane theory is a statically determinate problem. Okay. So, now the n theta z r is an algebraic equation. So, knowing the component of load along the radial direction and knowing the variation of radius of curvature r, we can find the n theta at any angle that is measured from the crown. Okay. One thing can be noted that the radius of curvature r is not constant except in the circular cylindrical shell, which is having constant radius of curvature, but other case of directrices the radius of curvature have to be first obtained by the theory of calculus. Okay. So, from the third equation we get n theta is equal to minus z r. Now, if I substitute this n theta minus z r in this equation, then we are targeting to obtain this n x theta. So, we get ultimately, if I take del n x theta by del x in the left hand side and transfer 1 by r del n theta by del theta in the right hand side with a negative sign, and capital Y is also in the right hand side with negative sign. Then after integrating we can get, because this n theta and y, this will be a function of theta. So, I group this together because r is also a function of theta and it is integrated with respect to x, because this differentiation is with respect to x. So, integrated with differentiation integrated with respect to x and the constant of integration. Now, since this expression is depending on the theta, so therefore, we are taking a constant as a function of theta. So, since this is not depending on the x, so I take it as a constant, but it is not purely constant, it is depending on the variable theta, but not with x. So, therefore, when I integrate it, it becomes minus k x plus f 1 theta. Actually, k is your this quantity 1 by r del n theta by del theta plus y. Okay. From equation 1 is this. So, once we got this n x theta, then we substitute this n x theta in the 1. This equation is 1 is written here again. So, you can substitute this del n x by del x is taken on the is kept in the left hand side. In the right hand side, the quantity is 1 plus r del n theta x by del theta is transferred with a negative sign, and also plus x is transferred with a negative sign. So, now this expression has to be integrated. Integrated this expression, one can obtain this n x equal to integration of 1 by r del n x theta by del theta plus x integration with respect to dx plus f 2 theta. F 2 theta is another constant of integration. Now, this quantity, that is here n x theta, we earlier obtained. N x theta is obtained as minus k x plus f 1 theta. So, we substitute n x theta here. When you substitute n x theta here and carry out the differentiation, then we obtain 1 by r del by del theta bracket minus k x plus f 1 theta plus x. X is the component of the load along the x direction, along the longitudinal direction, that is the direction parallel to the generator. Okay. Plus constant of integration f 2 theta appears. Okay. Now, integrating this expression, we get now, you see here k is a function of theta. So, therefore, dk by d theta is kept here, and x is not x is integrated with respect to dx, x is integrated here. So, after integrating this quantity x, it becomes x square by 2 and r is there. So, first term integration is carried out, second term integration you can see this df 1 by d theta term is appearing here, and integration of this 1 with respect to x is x, and 1 by r term is appearing here. Okay. Then the third term is capital X, which is the component of the load in the longitudinal direction, that is also a constant quantity. So, its integration will be minus capital X into x plus the constant of integration is there. So, we have obtained the three expressions of the stresses individually. One is your n theta is z r, okay, that is the first stress. This circumferential stress is easily obtained without solving any differential equation, because the third equation of equilibrium is an algebraic equation. Then secondly, we got n x theta, which is given by minus k x plus f 1 theta, and lastly we obtain the longitudinal stress n x, which is given by x square by 2 r dk by d theta minus 1 by r d f 1 by d theta into x minus capital X into x plus f 2 theta. So, here the task remains to find out the differential coefficient dk by d theta, and also to evaluate the unknown constant f 1 and f 2 theta by substituting the boundary conditions. So, we shall illustrate one type of boundary condition that is possible here to implement. Other types of boundary condition requires rigorous solution, and that is not possible with this membrane hypothesis. So, here we obtain this stresses and we found the unknown constant f 1 theta and f 2 theta make their appearance in the expression of the stresses. So, let us find out the unknown constant f 1 theta and f 2 theta. Now, at the traverse when this shell is supported, we take n x equal to 0. That means, boundary condition is from the assumption that traverse will not receive any loads applied normal to their planes. So, based on that condition we take n x equal to 0, provided we take the origin at the center of the shell. So, if the span of the shell is L, then at x is equal to plus L by 2 and x is equal to minus L by 2, two traverse are there and there the n x is 0. So, substituting this boundary condition that n x is equal to 0 at x is equal to plus L by 2 minus L by 2, we can get one constant. The second boundary condition is n x theta is 0 at x is equal to 0, because x is equal to 0 is the point of symmetry and there the shear force cannot exist. So, for most of the shell occurring in practice, the load along the x direction, longitudinal direction is also 0. So, therefore, we obtain the two constant of integration. One is n x theta is 0 at x is equal to 0, that means f 1 theta equal to 0. Applying the first boundary condition, that is the second boundary condition on n x theta we applied. First boundary condition was on the n x and the n x was the longitudinal stress, which is 0 at x is equal to plus L by 2 and minus L by 2, and taking the component of the load along the longitudinal direction capital X equal to 0. We now put this x is equal to L by 2 here and then let us evaluate f 2 theta. So, f 2 theta can be evaluated by putting x is equal to L by 2 here, and we get that n x f 2 theta is nothing but minus L square by 8 r into d k by d theta. Okay. Hence, the expression for the stresses becomes n theta is equal to minus z r, then n x theta is equal to minus k x, because f 1 theta is 0 and f 2 theta we have evaluated as minus L square by 8 r d k by d theta, and this is when substituted in the expression for n x, we can simplify this expression as n x equal to minus 1 by 2 bracket L square by 4 minus x square 1 by r d k by d theta. R is the radius of curvature at the point of shell mid surface, and in general r is a function of subtended angle theta. Okay. Now, in calculation of membrane stresses, some steps have to be followed. So, systematic steps are given here for the given directrix and geometry of the shell. First, find this x, y and z and also the expression for radius of curvature, that is the most important. So, that task have to be done completed first. Given the load in any direction, we have to find the component of the load along the longitudinal direction, along the directrix and along the radial direction. So, three component of loads are found and also the radius of curvature of the directrix curve is to be found out. So, once these quantities are found out, then we go for obtaining n theta. N theta is the circumferential stress that is developed on the shell. So, n theta is equal to minus z r. So, this is simply found from the algebraic third equilibrium equation, which is an algebraic equation. Then after finding n theta, find the value of k, because you are seeing that k is appearing in many places. So, we have to know what is k. So, after finding this n theta, k is to be obtained and k is nothing but 1 by r d n theta by d theta plus y. Okay. Once k is obtained, then go to this step, find n x theta is equal to minus k into x. Then after finding n x theta, find the value of n x, because n x depends on the x. So, x can be fixed at any location, and then the k is already evaluated here. So, k is in terms of theta. So, therefore, 1 by r d k d theta can be calculated and n x is completely known. Okay. So, today we have completed the derivation of the differential equations of equilibrium of a cylindrical shell and using the membrane hypothesis. And it has been seen that 3 unknown membrane forces are existing in the differential equations, and there are 3 differential equations also. So, this problem is a statically determinate problem, and we have attempted a general solution for the equilibrium equations for simply supported boundary condition. What I mean that it is a general equation, general solution whatever be the radius of curvature and loading, that means depending on the directrix, whether it is a arc of a circle, whether it is a semi ellipse, whether it is a cycloid, whether it is a parabola, whatever may be, we can give input to this general solution required quantities. Required quantities are radius of curvature and the value of x, y and z. So, after giving this input, we can derive the equation or expression for membrane forces in the cylindrical shell for any type of directrix. Any type of, there is no restriction that it should be a circular cylindrical shell or it may be a paraboloid shell, any type of directrix you take and this expression can be used. So, this solution will be used to find the stresses in our next class for shells of different directrices under the action of dead load and live load. Thank you very much.